All right, let's talk about Arzelà-Ascoli, which is this the first of these theorems that are sort of like, well, maybe a second one. I guess we proved the thing for countable sets. Is sort of bounded implies existence of subsequences. So this time, this is for continuous functions. And so, what does it say? And that we're going to prove two different things: one for convergence on a compact set, and one for uniform convergence on a single compact set, and one for uniform convergence on compact sets. So it's really about compact sets, uniform convergence on compact sets. So can start with a single compact set. And what does it say? Well, it says that bounded and equicontinuous implies existence of convergent subsequences. Now, the more important things is the if you have bounded and equicontinuous, that you have convergent subsequences, but also you get as a sort of byproduct, or actually we'll prove that first, is that you get you only need pointwise boundedness, and then equicontinuity gives you uniform boundedness, and together with pointwise boundedness gives you uniform boundedness, and then from that we'll also get that you get uniformly convergent subsequences, again using equicontinuity. So basically that's the difference between a straight sort of analog of Bolzano-Weierstrass, right? You can't just have bounded. We need some sort of uniformity in that. If we're starting with a sequence, we need some sort of uniformity in how continuous it is, right? So, well, we will want to use this lemma for countable sets. We'll stick in a sort of a large enough countable set, and we'll use it to get subsequences. So first, we need to figure out that we can put in sort of large enough countable subsets that take up a lot of space, but are still countable. Take up a lot of space. They're sort of everywhere. They don't really take up much space because they're just countable, but they're sort of they are everywhere. So by that we mean that they're dense. So this works in any metric space. If we have a compact metric space or a compact set in a metric space, there exists a countable dense subset. That is, there exists a countable subset whose closure is all of X. So first, because we haven't used this notation before, so in a general metric space, we'll write B of X and delta to mean the ball of radius delta. So all the points in the metric space that are within delta of X. Now, this is a compact metric space, so there has to exist finitely many balls of any radius that cover it. So, for example, for every natural number, there are finitely many balls of radius 1 over n that cover all of X, right? So take such a collection for every n, right? So we're gonna get finitely many centers, right? There are going to be k sub n of them, but so for each n we might get actually as n grows, the k sub n is going to grow as well. But we're going to get just finitely many that cover all of X, right? So now our countable dense set is going to be the set D, which is just these centers, right? And we're going to just put all these centers together for all different n, right? And it is clearly countable. It's a countable union of finite sets, so it's countable. Now, why is it dense? Well, suppose that you have some x in your metric space, and you take any epsilon. If we can show that within that epsilon there is one of these centers, then we're done. And well, it's like exactly the way this works, right? Because for any n, we can pick an n large enough so that 1 over n is less than epsilon, so that we're gonna get this sort of inclusion, and we can pick a center of one of these balls, right, that are in D, such that x is within it, right, within 1 over n, right, is in one of these balls, right. Well, that's because once I've chosen an n, I just look at the balls of that radius, and x is in one of them. Okay, well, that means that x is in the closure of D, and D is dense, right? So, all right. So now we can move to Arzelà-Ascoli, at least for compact sets. So suppose that we have any compact metric space, right? And let f sub n is going to be a sequence, so complex valued functions that is going to be pointwise bounded and equicontinuous, right? Now, the conclusion is that the sequence is first uniformly bounded, and that's maybe not the important conclusion. The important conclusion for us is that f contains a conversion. F sub n contains a convergent subsequence, uniformly convergent subsequence, right? So that's Arzelà-Ascoli for compact metric spaces. So let's prove this. So first, X is compact, so the sequence is uniformly equicontinuous, right? Automatically. Now, what that means is that we have this delta epsilon, right? So pick, given an epsilon equal to 1, so we're going to prove uniformly bounded. So just 1 is good enough, and you can use any number that you want, but why not 1 then? And we're going to pick the delta that corresponds to that epsilon, right? What does that mean? That means that one way to write down that inequality is this way, right? Is that within if we look at the ball of radius 1 around Fn of x, then we get, and we look at all the points that map to it, it must include this whole ball of radius delta around x, and this should work for any x in the metric space and any n, right? So that's just uniform equicontinuity. Now that we have this delta, and we have these delta balls, right? Well, we can cover x by finitely many of these, right? So maybe this k is very large, but it's finite, right? Because it's, again, x is compact. So now we use pointwise boundedness. Now we have finitely many points, x1 through xk. So we can bound this sequence at those points, and we can just choose the maximum of those bounds. There's finitely many, so there exists a single m such that the Fn in modulus is bounded at x1 through xk, right? So now pick any x in our metric space. It's gonna be in some in one of these balls, because these balls cover x, right? So therefore, we can again rewrite this in yet another way. What does it mean? Well, it means it's giving this inequality, right? you have 2 points x and x sub j, and they're within these guys are within delta of each other, right? So therefore we have this inequality for all n, right? That's the way that delta was chosen. Well, you just use triangle inequality, actually the reverse triangle inequality, to get a bound on the modulus of f sub n of x, right? And that's bounded by 1, which is this 1 over there, right? Plus, however large the f sub n at xj was, right? And that's at most m, right? So we get a uniform bound, right? This m is fixed, right? It didn't depend on x. So the sequence is uniformly bounded. Okay. Now we want to figure out our conversion subsequence. So take dense countable subset D of X and find a subsequence that converges pointwise on D. And to make things easier, let's just call this subsequence G sub J, just to have a simpler name for it. And we're just gonna talk about this sequence G sub N or G sub J, right? Now this sequence is uniformly equicontinuous, right? Well, I mean, it's a subsequence of a uniformly equicontinuous sequence, right? So that means that given any epsilon, any positive epsilon, there is a delta, a positive delta, such that, and again, we're doing basically the same thing as over here. We're just doing it for, well, now epsilon over 3, right? And with Gn, right? So for all n, we get this containment, this inequality. All right. So let's scroll that up a little bit. So if I have now any x in the metric space, it's in some delta ball of some y that's in D, right? Within delta of something in D, right? Now I can use that delta, again a different delta than above, right? We can cover X again by compactness by delta balls, right? Finitely many delta balls, and what we can get is that there exists some large capital N, such that for all n and m, little n and little m, if I look at basically I look at the Cauchy bit of the estimate, or the estimate for Cauchy sequences, right? On these xj, right? There's only finitely many of these x1 through xk, right? So that means that and we have that this sequence, it converges pointwise, right? So we can do it, at finitely many points. We can pick one such n, right? Such that this is true, right? So now we just need to do it at all x, right? So, well, if we have any x in x, there is a some j such that it's within delta of that xj, right? Because again, it gets covered. So that means that for every L, we can we have this is going out here again, right? This is where we use that epsilon over 3, right? That we get that GL of x minus GL of xj, right? That this is within epsilon over 3, right? We're using uniform equicontinuity, right? Because x and xj are within delta of each other, right? So that means that for all n and m bigger than n, we have the following inequality, right? I mean, this is what we want for showing Cauchy, right? And now we're doing uniformly Cauchy, right? This n does not depend on what x we've chosen, right? So we're looking at this estimate, and then we rewrite it, using triangle inequality as these 3 moduli, right? So we basically first look at n, and we go from x to xj, right? And here we can use this estimate over here, right? And the same thing for this last one. If we go if we sort of go from this g sub m from x to xj, again, this is within epsilon over 3. Now, in going from gn to gm on xj, well, here we can use this estimate over here, right? That was coming from this being Cauchy uniform Cauchy at those finitely many points, right? So I get, because those are all 3 are less than epsilon over 3, that this is less than epsilon. Well, that means that we're uniformly Cauchy, right? That there is a single n that works for all x in x. Well, because C is complete, that means that it's actually uniformly convergent, right? It's by completeness you get that that there is an actual limit, right, at each point, right? You get by completeness you get pointwise limits, right? And because it's uniformly Cauchy, you get uniformly convergent, right? Okay, so that's the proof, right? Now let's look at the version of Arzelà-Ascoli that we'll need for open sets. So this is not just when we have a single compact set, we really have any compact set in an open set, really. So let's suppose this is just for subsets of open subsets of the complex plane, and we look at a pointwise bounded and equicontinuous sequence of complex valued functions, right? Actually, now I see a slight typo. This should be u, not x. So then f sub n contains a subsequence, converges uniformly on compact subsets, right? So let d from z to boundary of u, let that denote the distance to the boundary. Now we're gonna want to exhaust u by compact sets. So let's define these sets k sub l be a set that, well, we're at least 1 over L from the boundary, and we're no further than L from the origin, right? Now, because, well, this is going to be continuous, this is going to be a closed and bounded subset of the complex plane, and so we have a compact set, right? It's closed and bounded in Euclidean spaces does mean compact. Again, you don't want to ever think that closed and bounded is the same thing as compact, but we are in, it's a closed and bounded set in C, right? So, all right. Now, U is a union of these sets. Well, that follows from the definition. Every point is some fixed distance from the boundary and some fixed distance from the origin. So for some large enough L, it's going to be in some case of L. The interiors, let's maybe take some a little bit of thought. The interior of this case of L is actually this this set where we basically replace the non-strict inequalities with strict inequalities, and I noticed another typo over here. This should of course be the opposite inequality. Sorry about that. Now, K sub L is within the interior of the K sub L plus 1 compact set, and that's just because these well, I mean, it's obvious one from these formulas, right? And further, we actually get not just that U is covered by these K sub L's, it's covered by the interiors, right? So it's an open covering. Now, Arzelà-Ascoli on compact sets implies that well, there exists a subsequence of f sub n that converges uniformly on K sub 1. Now, for the same reason, there exists a subsequence of this first subsequence that converges uniformly on K sub 2, right? And notice that this also converges on K sub 1, right? Because it's a subsequence of a sequence that converges on K sub 1, and so on. We keep doing this, right? So we get infinitely many subsequences. And now we consider the diagonal subsequence. Now, any compact set K is in the interior of some of these, one of these K sub L's, and that's just because, well, we have an open cover, right? So there is a finite subcover, and so this is an increasing sequence of sets. So any subcover is really just one of these. So we get that every compact K is inside some. It's in the interior of some K sub L. And it's really just all we need is that it's in some K sub L. Now if we look at a tail of this diagonal sequence, let's say the L tail, then it is a subsequence of the Lth subsequence, right? Because, well, that's when at some point n becomes L, and then we're just taking subsequences of that. So therefore, it's this subsequence, the L subsequence, is uniformly convergent on K sub L, and therefore on K, and therefore F sub N is also uniformly convergent on K sub L, and therefore on K, and we're done. So that's Arzelà-Ascoli for not quite compact sets, but open subsets of the complex plane.